In this video, I want to elaborate on the idea of an upper bound. So we already introduced the basic idea, but we're going to talk through this with some mathematical notation. So take a look at the graph on the right-hand side. There I have two arbitrary functions. One of them is red and one of them is blue. Let me go ahead and label them. So the red one, I'm going to call that my f of n. So maybe this is somehow the function that I'm trying to bound. Then over here, this blue function, I'm going to call it g of n. G of n is kind of another typical function name, right? So we'll just stick with g of n. So we have f of n and g of n side by side. Now, if I'm looking at this graph, we see a trend. That trend is that g of n is going to be, past a certain point, always larger than f of n. So this is basically our demonstration, our graphical demonstration of the idea that g of n is probably an upper bound on f of n. Now, of course, from this picture, I don't know for sure. Right? Presumably these functions go on forever, and right now I don't really have the evidence to say g of n is for sure an upper bound on f of n. In fact, right, if we think about mathematical terms, well, we haven't even looked at a definition for what something means to be an upper bound. So we don't really know for sure, but graphically we can kind of get an idea of what is maybe happening. So g of n appears to, past a certain point, always be higher than f of n. Now that particular point, we'll actually give it a name. So that we'll call x sub 0. So this little intersection here. Right? So these functions intersect a couple times, right? And there's sometimes that blue is greater than red is greater than blue. But past this particular point, right, past this x0 point, our g of n, right, our blue function is always greater than, or appears to be always greater than f of n, right? So this is kind of our last kind of point of intersection. It's going to be a particular point past which our upper bound idea holds, right? So upper bounds are always going to be expressed in terms of, well, they are good past this point. Prior to that point, I don't really know. The idea being is that all sorts of different things can happen with very small programs. Maybe you have some constant overhead, and that initial region, right, before this x naught or x0, right, this region over here, my analysis is basically going to be unpredictable because of these kind of little fluctuations that happen, right, or special cases that happen. So I don't really want to mess with that stuff. All right, so graphically, this is the idea of an upper bound, right? We have my g of n always above f of n past some region. So how do we define that mathematically? So now we're going to get our hands a little bit dirty. So I have the definition here, and I'm going to read it. Definition. We write that f of n equal O of n, right? And this is basically the proper syntax. F of n equal O of g of n. To say that f of n has an upper bound, right? Keywords there, of g of n. In general, right, whenever we write O of n, we're basically saying, oh, the thing on the left, right, f of n has some upper bound, and then inside of that O of n, right, the stuff in here, right, this is what's actually upper bounded by, right? G of n is just an arbitrary function, right? It could be anything in there, right? It could be n, could be n squared, it could be whatever. For now, we're just saying it's generic. Now, when we say that, well, we're upper bound, right, if we want to be more precise, we'll say that f of n, right, will take at most this number of operations, right? It won't ever take more time than what that upper bound is, right? We don't want that red line going above the blue line. That would be against kind of our intuition for what does it mean for something to be an upper bound. And formally what we'll say is the following. F of n equal O of g of n if and only if the absolute value of f of n is less than or equal to a constant c times the absolute value of g of n for n greater than x0, where x0 is some constant. So that would be our formal definition. Recall x sub 0 from our previous slide is that cutoff point, right, at which point the upper bound actually holds. Before then, anything could happen. After it, then we're good. So our main definition lies here. F of n equal O of g of n, if and only if. So mechanically what we're saying, right, is that f of n is big O, right? That's our kind of be our term for an upper bound. We'll say that it's big O. That's the common nomenclature. If, right, this right-hand side holds, right, this absolute value of f versus the absolute value of g. The absolute values don't really matter to us all that much. Remember that these are supposed to be growth functions that we analyze, right? And it doesn't really make sense for a function to take negative time, right, or negative number of operations. So in general, we don't really worry about those absolute signs, although in the mathematical kind of definitions thing, they are there, right, and so we should leave them there. They just don't really, complicate things for us in the practical world. And so what that bit of text there is saying, right, is that f is upper bounded, right, by g of n, if, right, f is always less than some constant times g of n, right? So g of n basically is some other arbitrary function, right? And then that function, right, basically is growing as fast as f, right? We don't want f to somehow jump up right in that graph and over and spring over blue, the upper bound function. We don't want that to happen. So g of n basically is obligated to always be above f of n. Now there's this little c value in there. That c value is a constant. Basically what that's saying is that in our big O, right, somehow, right, big O, right, is some function, right? It could be n squared, right? I'm actually allowed to have some constant in front of there that I can use to scale it. I can use to make it bigger, right? I have that coefficient, basically I'm allowed to play with it. Notice that c isn't assigned to a particular value here, right? It's allowed to basically change. So it's somehow a little bit of flexibility when we write an upper bound, right? So you can maybe picture that blue line, right? Maybe it could go up even higher, right? Or maybe it can even come down a little bit. I'm allowed basically in the definition to pick whatever coefficient I have on that function that I use for my g of n, right? I don't have to care about specifically what it is. I'm allowed to pick something that's convenient. So if I want to, I can make it really big, and maybe then it's easier for me to show that a particular g of n is actually the upper bound for an f of n. That's actually quite nice in terms of the math, right? It gives us a little bit of flexibility. And then of course x sub 0, right, is that fixed point after which my upper bound is actually supposed to hold. So that's our upper division. So now let's take a look at how I would actually go to a function and figure out what is the big O for it, right? What is the upper bound for it? So the process is pretty simple. Basically what we say is given some function f of n, drop all but the dominant term, and then drop the coefficient on the term that's left over. So basically we're just throwing away a lot of stuff. The result from that will be the big O upper bound for that particular function. Below I have a couple of examples. So let's say over here that my f of n is 2n plus 3. Well, try following our rules. First thing I want to do is drop all but the dominant term. Here that 2n is the dominant term because it grows. The plus 3 is just a constant. It's not going to do anything. So we drop this plus 3. Then we have 2n. Well, our second part of our rule there for finding big O, right, for finding this upper bound, is going to be to drop the coefficient. So I'll drop the 2. Result is that our big O of f1 is n. So over here, right, g of n, right, is equal to n, right? So maybe if I wanted to write the full syntax here, right, f1 of n is big O of n, right? When we wrote generically before, we said that f of n was big O of g of n, but now we know what g of n is, right? It's just n, so I can do a substitution there. So f1 of n, right, is O of n. Right, so that function there, right, 2n plus 3 is upper bounded by n, right, by a g of n equal to n. So it's a linear function being bounded also by another linear function. Now, of course, the reason why that works is because there's that free constant we're allowed in front of n, right? So I can actually pick something like, oh, hey, in g of n, right, that n maybe has a 10 in front of it, right? Well, if I have 10n versus 2n plus 3, well, for decent large values, right, that 10n is going to be much larger than 2n. So for sure it's going to be an upper bound that works for us just because we're allowed to pick that constant there. Now, if I wanted to prove that mathematically, I would basically need something like this over here. And it's rather simple here for this example just because we're using a simple function. But what we need to do, right, if we want to actually prove that that bound is correct, right? Initially what we talked through is kind of a heuristic process for figuring out what is the big O of a particular f of n. But what if I wanted to actually prove, right, that that particular bound is correct? What happens is that then I need to show that that definition up top holds. So that definition, right, was something like, f of n less than or equal to g of n, right? So what I would do, right, is basically try to show that these things work out. And basically there's some substitution stuff that happens, right? So over here, right, I have my left-hand side, right, is supposed to be absolute of f of n. Here, right, my f of n was 2n plus 3. And then this is less than, so let's assume these should be absolute bars here. Let me make these a little bit more obvious. Less than, and c times g of n. So c, absolute value, g of n we said is n over here, close the absolute. Right? So if I were just to do that substitution, right, based on my f of n and my g of n that I got from that basic process that was defined, then I have this expression like this. And this expression, basically, I need to argue that it is true. Right? And if I can argue that it's true, then I've proved the upper bound. In this case, it becomes mainly algebra. Basically what will happen is we'll drop our absolute values because it doesn't really matter for our practical examples. And then we'll basically say, oh, hey, I need to find out some value of C such that this whole thing is true. All right, pick some coefficient. And I can pick a decent coefficient here. Usually what you just do is pick that coefficient to be the sum of the coefficients of everything on the left-hand side. Maybe you can think about why that would work. And so I could pick C to be something like 5, right? 2 plus 3. That actually gives me this expression down here that I've written in the slides, right? And then in this bound, right? This bound will hold, right, for some sufficiently large values of n. And what I can actually do is I can actually solve that thing for n and basically figure out, what is going to be the cutoff by which it applies, right? So in this case, we're saying that C is going to be equal to 5, and this cutoff, right, this upper bound will apply for n greater than 0. Let's assume that n is an integer type, so basically what we're saying is that 1 or greater, this thing will hold. Okay, so that's a simple example of showing that our bound holds, right? So the basic idea, right, is that if I have a growth function, right, I can use that heuristic process to figure out what the big O is, right, and that gives me a suggestion of what it is. But really, right, in terms of math, we want to show or prove, right, that that is the correct answer. And the way we do that is by basically showing that that definition actually holds. So let's just do one more example. Over here, right, I have my F2. F2 is log n times 35, n squared. Let's say I want to figure out the big O. What would I do, right, is I drop all but the dominant term. In this case, I'm dropping the log term. And then I drop the coefficient on the remaining term. Remaining term doesn't have a coefficient. It's really just 1 behind the scenes, so I can leave it alone. So F2 is going to be big O of n squared. And again, I'm just writing the kind of the proper notation that is also correct. So F2 is O of n squared. Okay, so we have that. On the right-hand side, again, you have kind of the derivation to show that that's true, and it's following the same process as we did for the last function. So basically, we look back up at the definition, f less than g of n, right? Fill in our blanks, right? Our f of n we know, our g of n that we're guessing by doing that elimination of terms. And then we figure out, what is the value of c by adding all the coefficients on the left-hand side. That gives us an expression, and then we can basically just solve for n, right? Figure out when is this thing going to hold. So it's not too bad for these simple functions. When you're doing something maybe with a more complicated function, then it'll take you a little bit more time. But the overall process, right, will be the same. Maybe there's just more algebraic steps involved. Okay, so big O, right, again, is this general term, right, we use when we're saying that something is an upper bound, right? So I have f of n, right, some growth function, and I'm deriving here my upper bounds for that, right, which is a big O expression. Keep in mind the big O is always above another function. This is good because it gives us kind of our worst case, right? We know our programs are going to take longer than this amount of time, but on the negatives, right, big O is basically really easy to write because we can just say things like, oh, something is big O of 2 to the n, right? Something that's exponential. Well, obviously, my program is going to be big O of that, right? That function grows so quickly that pretty much everything that I could write, right, in a program will take less time to run than that. So sometimes people kind of wave their hands and just make their upper bounds really big, but that's not useful for us. Really what we want to do is you want to make a big O, right, a upper bound that's as close as we possibly can be to the actual f of n, right? That gives us kind of more information. It's closer to it. Something that's really large, right, is just kind of like waving our hands, and there's just so many functions that are less than it that doesn't really tell us anything about that f of n. All right, so I have one final note here about upper bounds, and that's about the use of logs. So it would be true to say the following. Log sub 2 of n is big O of log sub 2 of n. Also, log sub 10 of n is equal to O of log sub 2 of n. So I have basically my left-hand sides are different and my right-hand sides are the same. So I'm saying two different logs resolve to the same big O's, resolve to the same upper bound. Take a moment and ask yourself, why might that be the case? Okay, so the answer there is simply put, log conversion is a constant time operation, right? So if I want to switch from log 2 of n to log 10 of n, right? If I want to do a change of base operation, I basically just divide by something like, I don't know, log of 2 over of 10, base 10 or something, or log base 10 of 2. All I need to do, right, is that constant time operation, and that constant time operation, basically what happens is it gets folded into the constant within the definition of big O. So over here I have this c value here. That c value is allowed to be anything, right? So that value there basically can soak up the conversion, right? The little constant, right, that results from a change of base operation. So in big O, basically we can be a little bit lazy and say that all logs look the same, right? Because constant times change those bases, right? And that constant time just gets folded into that c in the definition of the function. So they're all the same from the point of view of an upper bound.